Okay, hello everybody and welcome to another lab hangout. I am snowed in today, so we're gonna talk about some audio stuff. I'm changing up the format a little bit in that this is actually a pre-recorded show, but it is unscripted and live. It's just that it'll be uploaded to YouTube post-recording. So maybe we'll get back to the live format at some point when my internet is better and my laptop is better. But enough about me. Let's get right to the audio stuff, and let's start with a safety tip. This is a 10,000 microfarad 50 volt Nishikan capacitor with this is like one of the golds, fine golds or something. I don't even want to know what the price on this capacitor was. And as you can see, if we look at the cap there, you can see that I have blown this one up, and I did that by exceeding the voltage, the rated voltage of the part, and what happens is the part gets really hot and it swells and a whole bunch of junk explodes and flies out of the top here, and it made a loud pop, and there was a big puff of gray smoke. And it took me a second to figure out what was going on, and I was reaching for the fire extinguisher when I realized what had happened, and so there was no actual fire, but it was pretty dramatic, and I wish I had been filming so I could show you, just just for your own safety, because these things happen. And what happened in this case was I just had it in my head that these were 100 volt caps, and of course they're not, and that's what happened. So I have since replaced the capacitors in my prototypes with 100 volt caps so that I can experiment with larger voltages. And 50 volts was, that was just fine for all the amps that I had made previously, but I was trying to get a 2SK182 to behave itself, and so I was cranking up the voltage, and that's what happened. So there's this week's safety tip. So speaking of the 2SK182, here it is. We've talked about it a little bit before, and we'll talk about it just a little bit this time as well. Starting with a little bit of data. Unlike the Sony chips that there's not a lot of data out there, no data sheets or anything like that. I was able to find a little bit of data on the 2SK182. Gate to source voltage is 70 volts. Gate to drain voltage is 600 volts. It's a 600 volt part. Drain current 60 amps. It's 500 watts. So it can dissipate. This package can dissipate 500 watts. Gate leakage current, more on that later, is 100 microamps. And voltage amplification is 10 at 0.1 amp minus 20 gate voltage. And the amplification factor, like many SITs, increases with the drain to source voltage. So the figure, you have to, if you find a spec sheet on one of these, you have to kind of watch. The mu may not be what it states in the region where you're going to use the part. So you have to look at the curves or evaluate that for yourself. Input capacitance 2500 puff, that's at VGS equals 10 volts. And that also varies with the drain to source voltage. So it's something you have to evaluate in your particular circumstances. So I made a set of curves for the 182, and they look like this. And this is these are 5-volt steps, so this is 50 volts, and it's 0.2 amps per division. So this is an amp, and this would be 2 amps up here. And these are 1-volt steps. And I had built up a little light bulb amp, and I had made these curves, and I commented on a previous show that that I was a little bit disappointed, and I was. I mean, because that's a lot of gain variation in the region where I'm going to build a little light bulb amp. That doesn't mean this is a bad part. In fact, it looks a lot better at higher voltage, and we'll get to that in a second. But you know, if you're building a little light bulb amp or something like that, you know, this is probably not going to be your first choice. You know, to a certain extent, it is what it is, and unless we're gonna apply a lot of feedback or do some push-pull things or something like that, that's what the characteristics look like for this. And just for comparison purposes, this is the 2SK180, and it's a slightly different scale, but this is 50 volts, and this is 2 amps, and you can see that there's a lot less gain variation with this part in the region where I might, you know, build a light bulb amp. So what else do we know about the 2SK182? Well, let's see. Here is a temperature graph, and you can see that we have this sort of positive temperature coefficient below a couple of amps, and more on that a little bit later as well. But you can see that up here it's negative, and what that means is that if we're at 25, if the part is at 25 degrees C, and then it heats up to 100 degrees C without changing the gate voltage, that the temperature comes down, and that's generally a good thing, because what we don't want is we don't want the part to heat up and the current to go up as the temperature goes up, because that becomes a cycle. The temperature goes up, the current goes up. Temperature goes up, the current goes up, the temperature goes up, the current goes up. That's thermal runaway, and we don't want that. So you know, if we build an amp with this part, we might have to address that, and especially if we decide to build an amp with, you know, lower drain current, that might be something we have to deal with. So there's that. Input capacitance, they're both here, the 182 and the 180. And if you look at, you know, the 182 it's a bigger part, and so not surprisingly it has a lot more input capacitance, and you can see how it changes with the drain voltage. And so it's about 10,000 at 1 volt, and about at 100 volts it's what, about 8,000, something like that. That's quite a bit. The 2SK180 is a little better. It's about 3,000 at a volt, and here it is at I don't know, 2,700 or something at 100 volts. So that's a fair bit of input capacitance for either part, and the reason we care is that our signal generator, or our a CD player, or our preamp has an output impedance, and that output impedance along with this capacitance are going to form a low-pass filter. And if the output impedance of your source is sufficiently high, it will negatively affect the frequency response of your amplifier, and you may not get the bandwidth that you want. So so we have to address that sometimes, and we can address that by lowering our source impedance, just by having using a source with lower output impedance, or maybe a buffer or something like that. But it's a factor, so there it is. Okay, so I drew this up. This is the 2SK182 at high voltage, and the first thing I want to note is that this graph starts at 100 volts. I mean, this is 100 volts, not even showing 0 to 100. And this goes to 600 volts, and if I covered this up, you might, this almost looks like a 300B or something like that. Except that these units are amps, not tenths of an amp. These are amps. So this is a heavy duty part. And but what you can see is contrary to this situation, things are looking a lot more uniform. But look, I got to get way out here, right? 200, 300, 400 volts. And so, I don't know. I suppose there are different situations where we could use that. Maybe we put a bunch of these in parallel and make ourselves a 1,000-watt Class A amplifier and use these in a follower or something like that. Or maybe we use it with a transformer. We like a 300B. We use it with real high voltage and low current, and use it that way. So that's a possibility. And I may try some things. I'm not going to just give up on this part, but it's not. It's not going to make a great little light bulb amp. So there it is. So I got some questions after my last lab hangout, and some questions about current and voltage curves, and what those mean and what we can do with them and things like that. And also, there was some concern when I wasn't as thrilled as I needed to be, I guess, about the 2SK182. And again, I was talking about using that part in one particular application. That doesn't mean it's a bad part. It doesn't mean that other people haven't used them effectively. Thank you for sending me the schematics of other people's amplifiers and things like that. I appreciate that. But a lot of those were complicated amplifiers, multi-stage complicated amplifiers, and that's not the kind of amplifier that I build. So why do we care? I mean, why do we care about this non-uniformity, right? Well, it matters. It matters because, ostensibly we don't like distortion. And that's what this represents. If this is the region where we're going to use this part, then this variation in spacing represents variation in gain, which is going to cause distortion. And it would be helpful, I think, to talk about why does this cause distortion, and we can do that. Let's do this. We'll do this a little bit backwards. This is a normal sine wave. You're familiar with this, and in this case, it swings from plus 1 volt to minus 1 volt, centered around 0 volts. So that's a normal waveform, and this would be this might be our unamplified input signal, right? And this is a picture of a waveform, the same waveform with 17% second harmonic distortion. And I made this in Excel. You could do this too. You can make the, just draw these in Excel, and add different cosine waves together, and get any amount of distortion or number of harmonics as you might want to look at. But I deliberately chose a lot of second harmonic distortion, so that you could see what is happening to the waveform. And you can see that it's sort of offset, and that it's squished here and sort of stretched down here. And that's what second harmonic distortion looks like, and this is a good bit of it. So remember what that looks like, and we'll come back to that in a moment. Okay, so here we go again. These are our IV characteristic curves, and this is not a real. There we go. This is not a real. This is not a real part. This is just something I've made up. So it's not a real transistor. In fact, it's it's perfect. This is an idealized example of a static induction transistor. Okay, and these are all perfectly spaced, and they're all parallel to one another. We've talked about it before, but it bears probably repeating that the way these curves are made is we hold the gate at some voltage. So we present minus 2 volts, for example. We present minus 2 volts at the gate, and we hold it there. And then we sweep the drain voltage. So we sweep the voltage at the drain, and as we sweep the voltage at the drain, look what happens. I'm coming across, and all of a sudden my current starts to go up. Okay, and that's how we make these curves, and then we make a trace for every value, every different value of gate voltage that we're interested in. Okay, so that's how those curves are built. And a curve tracer is just an instrument that does all that work for you very quickly, and it's a handy thing to have, but by no means necessary to make little amplifiers and have fun. So this line here is what we call the load line, and it represents some resistance or impedance that is attached to the drain of this device. And if we want to know what the value of that resistance or impedance is in this particular case, we just this is about 60 volts, and that looks like about 10 amps, and we just apply Ohm's law, and that's about 6 ohms. Okay. All right, then we get to, we're familiar with kind of using these curves to tell us how the transistor is going to act under DC conditions, how our amplifier circuit's going to work under DC conditions. We want to know what the idle current is given a certain drain to source voltage, and given a certain gate to source voltage, right? We get that, and we know what our operating point is, or Q point. In this particular case, in this example, it looks like about 30 volts and 5 amps. Okay. So that's our Q point. Here's our load line. Our Q point lies along the load line. But we can also, we've talked before about how changing the gate to source voltage changes the current through the device. And that, that works for DC. Of course, it also works for alternating current. So if I take a signal and I apply it to the gate and it varies the gate, what's going to happen? Well, it's going to vary the current through the device. And if I've got a resistor in series with that device, the current through that resistor is going to change. And what happens when the current through the resistor changes? Well, the voltage across the resistor changes. So if I put in a few volts and I get out a lot of volts, I have amplification. So that's how amplification works. And if you look at our curves, and we can actually superimpose an input signal onto these gate to source voltage traces, okay? And you can see here our signal, our input signal, starts to go positive, and so we start to go more positive on the gate here, our Q point is -3, and we're going to swing to -1. That's more positive. And then that swings back down to -5 volts, and then back to -3. So that is 4 volts peak to peak. Our input signal, 4 volts peak to peak. Okay? Now what we can do is we can see how that affects the output. For that same 4 volts peak to peak, we can see what we get at the output. And it looks like we get a signal that swings from 30 to 20, so that's 10 volts, and from 30 to 40, 10 more volts, right? So 20 volts peak to peak. So 4 volts peak to peak in, 20 volts peak to peak out. That's amplification. Great. Okay. Now, that is, again, this is an idealized transistor. And you can see that this waveform is perfect. It looks just like, it's inverted, but it looks just like the input. Okay, and that's because there's no variation in gain. This is the region. If this is the region where I'm using this part, there's no variation in gain where I'm using it. So theoretically, no distortion. So what happens when I try to do this with a part that has a lot of variation in the gain? Well, same situation. I'm swinging from same Q point, same everything, different transistor, a more realistic transistor where I've got a lot of variation in gain here. And my input signal, same input signal. I'm swinging from -3 to -1, right? Down to -5, back to -3. Same input signal. But look what happens. My signal is squished here and stretched over here, right? And if I can find it, yeah, check it out. It looks a lot like that one. And that's what a second harmonic looks like. And we can even approximately quantify how much second harmonic we have made here by evaluating this asymmetry. And so our H2% is QB minus AQ divided by 2AQ plus QB times 100, right? And that ends up being 12 divided by 72 times 100 is 16.67%. And this is an approximation, and it makes a lot of assumptions. That it assumes that there are no other harmonics present, and so on. And this formula, it's as old as the hills, and it's been in all the old radio books and everything. But it does give you a pretty good idea of how how the amplifier behaves. Now remember, this is how it behaves at that voltage swing. So if you want to look at a watt, that's much smaller. But again, this is an approximation, and it a lot of times what we're interested in when we're designing is it a big number or is it a small number? We're not going to split hairs and worry about whether this is 16.61 or something. Sometimes you actually have to build the amplifier and measure it to find those things out. So don't make yourself too crazy about getting this number exact or these curves just right. Get an idea of how it's going to work, and then build the real thing and have fun. So hopefully that helps with explaining why I wasn't happy with the curves that I showed, and also why the curves at the higher voltages looked better to me. There are one or two other things to talk about. First of all, if you're going to work with these big token parts, they're not the package is bigger than a TO3, and so a TO3 heatsink won't work here. You'll have to re-drill your heatsink, or you can fashion a bracket like this one, and drill the holes for the larger package, and then some holes to attach this to your flat heatsink. You'll also need to make some thermal pads, and I made these. I bought a sheet of thermal rubber material, and I just punched holes with like a leather punch. And but since then, I realized that a solid state relay thermal pad will work just fine. And these are 49 cents on MPJA, so I could have saved a few dollars and used these. Well, the last thing I'd like to talk about is the 2SK180 light bulb amp. And if you just give me a second, I will queue up a video that I recorded a little bit earlier today. Okay, so we are looking at version 1 of the 2SK180 light bulb amplifier. It is single-ended, and you can see that there are two 300 watt light bulbs in parallel for the load, and I am using a 1 ohm source resistor, and we can talk about that in a minute. But there's the amp on the bench, and if we take a look at the power supplies, you can see that this is you have to double that figure on the left there. So this is a 60 volt supply on the drain, and we are at about 2.15 amps right now. That is going to settle in at about 2.25 after an hour or so. I've only been warming up for about a half an hour. and you can see the gate to source voltage is minus 5.3 volts. So those are our operating voltages and currents. And if we come over to the distortion analyzer, you can see that at 1 watt, 1 kilohertz, we're at about 0.156%. And this is about a 4 watt amplifier. And at 4 watts, it's around 1.5% distortion. And you can see it takes 1.473 volts of input to get a watt out of it, and that's partly because I am using that 1 ohm source resistor. And the reason I'm using that is, well, number one, it lowers the distortion a little, which is good. But I'm actually using it primarily because the 2SK180, at least the devices that I have, seems to have kind of a positive temperature coefficient below several amps. So we don't want it to run away on us, so I'm using that 1 ohm source resistor. We could bypass that with a big capacitor, and maybe I'll try that later and see what it does to the distortion. I mean, the distortion is going to go up a little bit when I do that, but we could try that. And if we look over here, you can see that the drain voltage right now, it's at 34 volts, and that's going to go down to about 33 volts again when it fully warms up and it's idling at 2.25 amps. So there it is, version 1. Oh, I also wanted to mention that my devices have about 50 microamps of gate leakage current, and so that is within spec for the part. I think it's the range is 1 to 100 microamps max, and that means that your devices are probably going to have some gate leakage current as well, and the gate leakage current goes up with the drain to source voltage, and so that means you're going to have to take your 47K input resistor out and use something smaller like 10K. I'm actually using a 5K resistor on the input right now. So there it is. I have no idea what this sounds like. I will have to put the other one together and evaluate that next time. Okay, so that is, I guess, version 1 of the 2SK180 light bulb amplifier. That's just about all I have for today, but please subscribe, and if you have comments or questions, you can include your comments below on YouTube. My email address is mike@audiohobby.com if you would like to contact me there. Thanks for hanging out, and get out there and build something.